When a semiconductor device operates, its crystal produces power, which results in the device heating up. Such heating leads to irreversible damage of the device's structure. Thus, the reliability of semiconductor devices' operation, for the most part, depends upon the cooling efficiency. We can simplify the thermal design significantly by using a thermal model. In this case, the difference between the temperature of the crystal and that of the environment is caused by the thermal flow moving from the crystal to the environment through the thermal resistance of the crystal body cooler and cooler environment. Such thermal resistance is measured in degrees watts. The total maximum resistance for crystal environment can be calculated using the following formula. The thermal resistance for crystal body and body cooler is indicated in the reference documentation. For instance, according to such reference documentation, for irreversible transistor, its thermal resistance for crystal cooler is equal to 0.94 degrees watts. This means that if the crystal generates 19 watts of power, its temperature will exceed that of the cooler by 9.4 degrees. The thermal resistance of the cooler can be calculated using the following formula. Just as an example, let us design a cooler for irreversible transistor. Let us assume that the dissipated power of the transistor is 26.4 watt. The cooler should help us achieve the maximum crystal temperature on the transistor of no more than plus 110 degrees Celsius, while the maximum temperature of the environment is plus 40 degrees Celsius. Let us calculate the crystal environment thermal resistance for irreversible transistor. Now let us find out the thermal resistance of the required cooler. Knowing this value as well as using the technical data on dependence between the cooler section and its thermal resistance, such data will be different for different supplies, we'll be able to easily pick the cooler that will be just right for the job.